Lucas Vega. I'm going to be presenting a method from algebraic statistics. It's going to be Fisher's exact test, which is the statistics, but via Markov bases, which is the algebra. Now, if statistics was just fine, then there would be no need to study algebraic statistics. So there's got to be a problem somewhere that motivates the introduction of algebra. And that problem is found in Fisher's exact test. But before I get into it, I want to introduce an age-old problem that's been on everyone's mind. You know, does the way you eat corn influence whether you like algebra or analysis? This is something that keeps people up at night. You know, I don't want to insult your intelligence by assuming you haven't thought of this before. You know, you can eat corn like rolling it right here, right? Or you can do kind of like a sliding pane, right? Does that influence whether you like algebra or analysis? Well, if you want to answer this question, you can take a random sample of math majors and organize the results in a table. See, we got them organized by how they eat corn and what their math preference is. We call this a contingency table. And it helps us answer if there's a relationship between these two variables, because you can use this table to answer, well, assuming that these variables are actually independent, how likely or unlikely is our table? If assuming independence, it turns out that our original table is very unlikely, then maybe there's a relationship between those variables. So since we're assuming independence, we can actually calculate the probability for every contingency table in a sample space. What would be in our sample space? Would be tables with the same row and column sums. So here are two tables in our sample space. This first table is our original one. Assuming independence doesn't look that crazy, but assuming independence, this table looks kind of wild. If we're assuming that these variables have nothing to do with each other, the table suggests otherwise. It's like, well, if it's definitely the case, if you eat corn in rows, you prefer analysis, and if it's in spirals, it's algebra. So the probability of this table, assuming independence, would be less than the probability of this table. And you can use this ordering to talk about the p-value. What is the p-value of our original contingency table? The p-value of our original contingency table is the sum of all the probabilities from tables whose probability is less than the probability of the original table. The p-value helps us answer how likely is our table assuming independence. So this is what Fisher's exact test does. It computes the p-value in a very direct way so for a given contingency table, it computes all tables with the same row and column sums. That's our sample space. It computes the probability of each of those tables, and then it sums up all the probabilities less than or equal to the probability of your original table, and that's your answer. But therein lies the problem. We have to compute all tables with the same row and column sums. Here's a contingency table, not from a large sample, only 132 people. How many tables with the same row and column sums do you think are in the sample space? The answer is 258,000. And this is a small table. What about a table like this? And then why stop at 2 dimensions? For large tables, I hope it's clear that computing all things in the sample space is computationally impractical. So for large tables, we can't do Fisher's exact test. Fortunately, there's an algorithm that allows us to approximate the p-value we get from Fisher's exact test. So from this point on, we're going to represent our contingency tables as matrices, so we can do addition. These 3 contingency table matrices are from the same sample space because they have the same row and column sums, which is what I have right there. And I want to show you something interesting. So we have 2 tables right here that are in the same sample space, and if I add this middle matrix to this table, I get that table. So this matrix allowed us to move from this table to that table, and similarly, this matrix, when you add it here, allows us to move to this table to that table. So the matrices in the middle are special. They're what we call moves. By addition, they allow us to move through our sample space. And the set of all moves for every contingency table, there's a special set of moves that we're going to informally refer to now as a Markov basis. The Markov basis is key to making the Metropolis-Hastings algorithm work. Here's Metropolis-Hastings algorithm. I'm not going to go through it, but I'm going to have it here if we want to go back and look at it. Instead, I'm going to give you just a breakdown of how it works. So you let U be your contingency table. The algorithm is going to run for t iterations. You can make t arbitrarily large. on each iteration, the algorithm is going to use the Markov basis to generate tables with the same row and column sums as your original contingency table. Once the algorithm's done, it's going to sum up the probabilities from tables generated by the algorithm where their probability is less than the probability of your original table. And it turns out, as the number of iterations goes to infinity, this value converges to the p-value that we get in Fisher's exact test. And because of that, for a large number of iterations, if you run this algorithm a lot, the p-value you get is going to get really close to the p-value of Fisher's exact test. And we note that this process is way faster than doing Fisher's exact test. So, okay, we have our solution. But we need this weird thing called a Markov basis, which leads to the next part of the talk, or the remainder of the talk. If we have a contingency table, how do we get a Markov basis for it? So, in the interest of time, I'm not going to explain the theory and then show you the method. I'm going to show you the method of getting a Markov basis and explain the theory as I go. You might get lost on some parts, but I'm hoping to tie it all up in the end. Some things may seem random. Okay, this is what we're going to use for our example. This table that had 250,000 row of the sample space of 258,000. We don't want to compute all those tables. Let's get a Markov basis. First, we're going to start by representing our contingency table matrix as a contingency table vector in a natural way. We're just going to take the rows, stitch them together, and make a vector. Hopefully that's clear on how we're doing that. Just we're stitching the rows together. Now we're going to introduce something called the sufficient statistics matrix. There's a sufficient statistic matrix. We're going to denote it A for every single contingency table. And for our case, the sufficient statistic matrix is this thing right here. I could talk a lot about the sufficient statistic matrix, and there's a lot of, a deeper conversation on it would make the method make more sense. But in the interest of time, I'm not going to do that. But I'm going to note one interesting property of this matrix that hopefully convinces you that it has some special connection. When I multiply, this is our contingency table vector. If I multiply it by our matrix A, I get that vector over there. What is that vector? That vector is actually the marginal sums of our contingency table. So it's all the rows and column sums of our original contingency table. And remember, our sample space is all contingency tables that have the same row and column sums as this one. So the matrix A is definitely connected to that in some way. So moving on. Okay, we're using a method from algebraic geometry, computational algebraic geometry, to help us get Markov bases. Algebraic geometry is about polynomials in a very loose sense. So if we're going to use algebraic geometry, we need to figure out a way to associate contingency tables with polynomials, and then go back from polynomials to contingency tables. And this is how we're going to do it. So we have two examples, U and V. U is our original example. I just made up V. And we're going to associate an indeterminate or a variable with each row of our vectors. And we're going to build a polynomial, or in this case a monomial, in the following way. P to the U is going to be the monomial of all these indeterminates multiplied together, and in each indeterminate is going to be raised to the power that's found in the same row as U. So let's look at T. We have T is raised to the 3. Why? Because in the T row, we have 3 in U. That's P to the U. And then P to the V is similar. For R, we have R is raised to the 27 because in the R row in V, there's a 27. Hopefully that it's kind of clear how we're doing that. Now we can also go the other way, get a polynomial and turn it into a vector. And the way we're going to do that is we're going to add and subtract the powers that are above the same indeterminate. So we have PU minus PV. That polynomial right there is associated with this vector. For instance, and the reason why is in the R spot, which is the very top one, 16. 16 is 43 minus 27. It's the power of R in the PU vector minus the power of R in the PV vector. And then we just complete this for the rest of the vector. Now, you'll notice that that vector doesn't actually correspond to a contingency table. I can't sample negative people, but having negative vectors is important for reasons why we'll see later. Okay, this is kind of like throwing people into the deep end right here. I'm gonna try and like break this down. If you're familiar with commutative algebra, what I've defined up here is known as the toric ideal. And they're very well studied, and because they're very well studied, they actually help us. But for those of you who don't know, let me try and break this down. The toric ideal, I to the A, is this space of polynomials. It's this infinite space of polynomials. And they have this property that every polynomial in this space can be written as a linear combination of polynomials of the form in the brackets. Polynomials p to the u minus p to the v, where u minus v is a vector in the kernel of A. Informally, we've all taken linear algebra, you can think about this as a vector space. And for every vector space, you have a basis. And the basis, it has the property that everything in your vector space can be written as a linear combination of things in your basis. However, so right here, these types of polynomials would be our basis for this polynomial space, except right now, there's an infinite number of polynomials that satisfy the condition in between the brackets. However, there's an algorithm from computational geometry that allows you to get a finite generating set for that polynomial space. It's called the Buchberger algorithm. And this is what we get. So these set of polynomials can be used to generate the polynomial space described there. Now, let's take a moment and recap our problem. We are trying to get a Markov basis for that table, right? And remember, Markov bases were like these moves right here, right? That allowed us to move through our sample space. So if you have that in mind, what we've done hasn't really made any sense. It's like, okay, how in the world is this related? We want to get, a set of moves, and we have a set of polynomials. Well, we're going to turn the set of polynomials back into vectors, like we did in the previous slide, and then we're going to reshape those vectors into matrices. What do we get? This is our Markov basis. This is the thing we need to run the Metropolis-Hastings algorithm. So that was really weird. It's like we wanted a set of matrices, and we did a weird thing with polynomials. And when we did the subtraction from the polynomials, we got this set of moves. Why did that work? Well, it's from a big result in algebraic statistics, which says if you have a Markov basis, or you have a Markov basis if and only if the set of polynomials that you get from it is a generating set for the toric ideal. So what did we do? Since it's an if and only if, that's a spoiler. So we found a generating set for the toric ideal, and we took the associated vectors, and that was our Markov basis. And so that's it. Okay, 4 acknowledgements. Are there any questions? I know it was kind of a lot going on.
Can you just scroll back to slide 14?
Sure.
I just wanted to read something again. I think it was 13. Well, I wrote it down, but
This one?
one back maybe. I don't even remember anymore. Never mind.
Okay.
I want to know if you cooked and served corn on the cob to get that table.
I did not know. If you're curious, this is actually an example I made up. But Dr. Smith told me they've actually looked into this. Or I came up with some ridiculous example like, I don't know, your preference of food and whether you like algebra or analysis as a joke, and then Dr. Smith started talking about corn. And apparently it's a real thing that's been studied, and there actually is some relationship between your math preference and how you eat corn.
Do you know which way it goes?
No.
Like something on the way.
How do you
works.
equal it? Maybe that's.
I
that's
was
what
trying to remember, but I'm not sure. I think in rows, kind of. But I do both,
I
so.
think we have a question, Rick, no?
Yeah.
Okay, so I don't know, but I just want to know your concern. While you were studying metropolis heuristic algorithm, sometimes this is also studied along with exception rejection algorithm. Did you use somewhere, or do you think that your work can be connected with exception rejection algorithm?
I'm not sure what an exception rejection algorithm is, but I'll say the Metropolis Hastings algorithm does informally like accept or reject things
Yep.
in when it produces the tables. Maybe that's what you're talking about.
Yes, because the Q that you have written there, that has the connection with that, so I thought maybe you have used somewhere.
Interesting. No, I'm not too familiar with that theory, but I get what you're saying, because what it does is it will move to another table
Exactly.
based on probability.
Based on the
Right.
probability that you have got.
And it will reject a table if one of the tables you get has a negative value.
Good.
So,
I have a question.
yeah,
The one where you defined.
the torque ideal?
Yes.
Yes.
How's it?
So sorry. Okay, we're getting there.
It's okay.
There we go.
Yeah, so you said, hey, look, gosh, there's gonna be an infinite number of stuff, but then now we can whittle it down to this finite amount. Is
Yes.
that because U minus V has to be in the kernel of A? Is that what allows you
What allows us
to narrow it down that way?
Well, not that in particular, because there's an infinite number of items in the kernel of A, because we're not just considering positive vectors, you could have negative vectors too. What allows us to narrow it down is this result in algebraic geometry called the Hilbert basis theorem. It says an ideal of a polynomial ring always has a finite generating set.
Okay. Thank you.
Any other questions? Okay, well, I want to say thank you. When I was reading, up on algebraic statistics, it's very much too much to think about, too much to figure out. I frequently found myself stuck between the hope and doubt. And it truly was way too much to think about. And if you know what that is, that's the song outside of Dr. Smith's door, the Statistician's Blues. And so I would have been lost without Dr. Smith, so thank you. And I also wanted to take a chance just to thank the whole department. I'm graduating and I've had an awesome time here. I almost wasn't even a math major and I've been treated very, very well here, so thank you.
And on that, I will say
And he had a brief softball career here.
Oh, it was from a picture.
Oh, and then he had a basketball career, women's basketball. They have to